Okay, cool. So thanks everyone for joining us today for our latest risk and compound events webinar. So today we're joined by Dr. Ben Hague, who's a climate scientist from the Bureau of Meteorology in Australia. He's a coast and estuaries expert and develops and communicates multi-decadal coastal hazard information to inform adaptation decisions. His work aims to bridge the gap between research and practice. So, for example, he co-leads the National Partnership for Climate Projections Working Group on Climate Services and User Needs. So I'll throw it over to Ben now. So just take it away when you're ready.
Great, thanks, Cass. And so I'd like to start with an acknowledgement of country, which is something we do in Australia to pay respects to the Indigenous lands on which we are coming from or meeting on. I'm coming from the lands of the Wurundjeri people of the Kulin Nation. And I also want to note that this week is NAIDOC week, which is a week where it's sort of the national, it's a week that's come out of a day observing Aboriginal and Torres Strait Islander peoples and their contribution to Australia. So today I'm going to talk about the role of tides and sea level rise in driving compound flooding in Australian estuaries under climate change. And whilst Australia is a large country with a lot of land, we generally live very close to the coast in, at least for Australia, reasonably large cities. So 14 of our 15 largest population centres are located on estuaries. And one of those is the Gold Coast, which is shown here with this nice picture from, I think it's on the top of one of the tall buildings, that sort of shows the coast and the estuary here. And so I wanted to start with a bit of background on coastal stuff because I know not everybody here might have necessarily looked at it that much. And I guess I also sort of want to raise the idea of, are coastal hazards intrinsically compound hazards? Because you've always got multiple, basically for all coastal floods, you have multiple processes contributing to it. So you've got high tide, you've got tides, you've got storm surges, you've got sea level anomalies and sea level rise, and we'll go through what each of these are over the next few slides. And I guess I'm sort of talking about this today, but a bit of all of them. Often when coastal people talk about compound flooding, they're talking about compound riverine coastal flooding. But how much more compound is it really just because you've got stream flow as well as the four other things which contribute to it? So from a coastal perspective, the primary driver of sea level variability on daily timescales and in many places also monthly and annual timescales are tides. And there's also variability on sort of multi-year timescales as well. And tides arise from the moon and the sun, although the sun is not pictured in the diagram, pulling the water of the earth in certain directions, and then the earth sort of rotates around those bulges. Obviously it's more complicated than that because there's land on the earth, and so the tides bounce on and off the land, and so there's resonances and all of these sorts of things. Storm surge is another common process. These occur over multiple days, and the impacts are normally at or around high tide. And so you can see here a diagram of sort of some data from Melbourne, where we had this storm surge event in 2023, and you can see that the storm surge here reached sort of about 80 centimetres for sort of a few hours, but then there was also some oscillations with other sort of processes in the Melbourne's in an sort of a almost semi-enclosed bay, and so there were some resonances and other processes there as well, which led to higher storm surges. And so the two others are sea level anomalies and sea level rise, and these are sort of similar, and they can be hard to distinguish depending on how you analyse the data and I guess partition the sea levels into the four components. Because I think the other thing that's probably worth mentioning here, and I'll just go back to this slide, is this black line is the observations and the blue line is what the tide is. And so the tide is effectively analysed as sort of a counterfactual where you don't have any weather or climate and often sea level rise, but again you can choose whether you include it or not. But this is really just comes about from fitting sums of sines and cosines to the observed sea level over a long time period. And so it's a Fourier transformation, but it's not really physical. It's really a statistical representation of a physical process that we can't measure. And so this then becomes complicated because everything else becomes not tide when you start looking at it. And so working out what part of a tide gauge signal is the storm surge, what is the sea level anomaly, and what is sea level rise is to some extent arbitrary. But there's obviously conventions as well that can be used for different applications. And so a sea level anomaly is a prolonged, usually around months, elevated sea level, usually due to climate modes of variability such as the El Nino Southern Oscillation. And so there's two examples of that here. Is that there's the impact threshold of threshold exceedance a Tuvalu, and you can see that in 1998 in particular, there was almost a whole year with no exceedances of this threshold, and that was due to there being a strong El Nino which suppressed sea levels in that area. Sea level rise is very prolonged, of order centuries sea level rise, elevated sea level, usually due to climate change, vertical land motion, or sort of potentially also other, and usually sea level rise and sort of melting ice sheets, melting glaciers, thermal expansion, but also potentially changes in weather patterns as well. And so you can sort of see in this bottom diagram of how these two sort of interact to sort of lead to higher than average sort of monthly mean sea levels. And so in the red stars, they are sort of multi-year. All the stars are La Nina years, which are generally associated with higher sea levels in Australia. But you can see that these large, so there were La Nina events there are a number of La Nina events in the 1970s, but most of the current records have been broken since then. And that's because you've got sea level rise occurring at the same time. And again, in Australia, these two processes are probably of a comparable. There's now been enough sea level rise that the sea level anomalies don't necessarily reduce you to the level that you had of mean sea level in the 70s anymore. And I guess streamflow may or may not be a coastal process, but it impacts coastal areas, particularly in estuaries. And so so here's an example. I've got these maps of Australia through, so we can work out where all these places are. So this is in Newcastle, and you can see, so in blue we've got the Newcastle port gauge, which is just inside the estuary, and then Stockton is just a little bit further up. They sort of stay the same and track each other throughout this event, but as you go further up the river, Hexham in green, Raymond Terrace in red, and then Green Rocks is further up the river, which you can't see on this map. You can see there becomes increasingly large riverine contributions to the water levels, but there is still some element of sort of the tidalness, the coastal forcing. And when there's not a riverine flood, it is actually purely coastal forcing in all 5 of these locations. So you can sort of see here that the stream flow matters, but there's certain times when it matters and others when it's not present at all. And I guess in some respects, wave run-up is a little bit similar to this as well. This is a process that it's sort of two processes. One is more around a mass transport of water due to the sort of the waves being pushed towards the shore, and then the other is sort of the wave running up along the beach as the energy dissipates. And these sort of occur over multiple days for sort of the setup component, with variability on order of sort of seconds for the wave run-up component. And this example was from when I was in Europe in 2024. What's interesting about this example is that these were taken 2 days apart at about the same tide height, but the water level was really different at the beach because, one, there was a 15 centimetre storm surge, but primarily because of the waves on the second day compared to the first day. And this is at Monte Rosso in the Cinque Terre, for those who know the Mediterranean. So today I'm going to talk about 2 case studies and 2 new data sets which have sort of enabled us to talk a bit about the compound flooding and the role of sea level rise and coastal processes in compound flooding. So the key takeaways are going to be about flood thresholds being critical because they dictate the combined additional water level needed for impacts, tides modulating the probability that other potentially compounding factors can lead to flooding, and thirdly, that present-day compound floods could occur with fewer contributing factors with sea level rise. And so, in other words, present-day compound floods can occur with become less compound, I guess, in the future. But then I guess there's also the flip side of that. Well, the future compound floods are also worse than the present-day ones. So why do we need flood thresholds? In short, these projections of sea level for Melbourne, which is basically like a 20-year time slice, just increased by an amount of sea level rise, which is very basic but good for this illustration. really that doesn't tell you a lot because you don't have any context about how high the sea level needs to be for you to worry. But if you then put in a line which corresponds to the record sea level for Melbourne, you see that you start exceeding the record multiple times a year with not very much sea level rise. And so now you have some context for what these projections mean in terms of impacts. And so here is an example of the sorts of impacts that you see from these I think it's 1.64 is the record for Melbourne, and we probably equaled it about earlier last month, but we're still waiting on the final result. I guess the other reason for why this matters is that we can also look at how return periods, annual exceedance probabilities, and exceedances per year change under sea level rise as well. And then again, being able to relate these to what the flood thresholds are, so we can talk about a 1 in 100 year event becoming a once a year event, and so forth. And so you can see here again, this is simplistic because we're just increasing everything by an amount of sea level rise. But if there's a 40 centimetre difference between the 1 in 100 year level and a 10 times a year level, well, with 40 centimetres of sea level rise, the present day 1 in 100 year level becomes a 10 times a year level. A second sort of application of flood thresholds is about, I guess, comes to this idea of tolerance and how often would flooding have to occur for it to become intolerable. And normally, if it was in person, I'd have a show of hands here, but I guess people can just think about, well, how often would this have to happen for it to be intolerable? I feel like for sort of this nuisance flooding, it sort of probably sits somewhere between once a week and every day as to when people won't tolerate it anymore. But here's a different event from the same location, but that had much higher water levels. And so it becomes a question about, well, how often would you tolerate these sorts of impacts? And again, it probably depends on whether you live in one of the apartment buildings or you own this shop, but probably around once a decade or once a year would definitely be an issue for a number of people in this community. And so both frequency and height and severity of flooding influence tolerance. And why this matters is that if you're going to look at extreme sea levels as, say, a 1% AEP event, you don't know a priori whether the 1% AEP event corresponds to the impacts at the bottom or the impacts at the top. Now, probably it sits somewhere in between, particularly with sea level, because usually you won't have a good sample of riverine influenced events in a sea level record, and usually the tide gauge that you're using for sea level is further downstream than where the impacts are. But there's also places in Australia where the 1 in 100 year level is very, very close to the high tide level because there are places with 10-metre tides. So that's sort of, I guess, the reason for why we need flood thresholds. And I guess this sort of then leads into, well, tides modulating flood hazards. And so Lakes Entrance is one of the other locations that we're going to look at as a bit of a case study. And as far as locations in Australia go, Lakes Entrance has pretty small tides and reasonably large storm surges. Now, again, maybe they're not that large compared to other countries, and definitely Europe, they're not as large. And yeah, maybe the tides aren't as small as they are in the Gulf of Mexico, but again, they are still reasonably small. But even then, you still get a really strong modulation of flood hazards by tides. And this is because if you look at the differences in the daily high tide levels, they vary from about 0.25 metres to about 0.5 metres, so there's a 25 centimetre difference. There's a similar difference between monthly high tides. So the highest tide in June is usually higher than the highest tide in March, for example. And then both of these are of comparable magnitude to the typical monthly maximum storm surge. And so tides have this regular variability within and between years, but storm surges are more random. And this also sort of matters when you look at how you can predict these flood events. And so here's an example of the same storm surge event occurring at two different locations. And again, I probably should have put a map in here. Stony Point and Lakes Entrance are separated by about 300k along, or 200k along sort of the southern coast of Australia, sort of along the same stretch of coastline. And so the peak storm surge at Stony Point was 0.67 metres, and at Lakes Entrance it was 0.62 metres. But the highest level at Lakes Entrance was when the storm surge occurred. But the highest level at Stony Point was about 5 days before the peak of the storm surge because it was when the highest tide occurred. And so this is because that it's at Stony Point or Western Port, this tide gauge here has a 2-metre tidal range. I think I can put the pointer on actually. Yeah, here we go. It has a has a 2-metre tidal range, whereas at Lakes Entrance it's more like 60 centimetres, and so the 60 centimetre storm surge will elevate water levels under most conditions. Whereas at Western Port there's a sort of there's a smaller number of days. The tide needs to be at a certain height for a storm surge to be able to lead to a high sea level. And this is sort of something that we'll come back to as well throughout this talk. And so these are the impacts which happened at Lakes Entrance during that event. And it's worth noting that there are no pictures of Western Port because there were no impacts in Western Port, because it was basically the highest in this event was just sort of a normal high tide, for want of a better word. And then this is what happens when you look at the highest tides in Lakes Entrance and the highest storm surges in Lakes Entrance, and how the convolution of those really is a pattern for how many flood days you have in each month. And so the highest tides occur in June and July. The highest number of flood days occur in June and July. The highest number of storm surges occur in May, July, well, basically not June and a whole bunch of other months. And so there's obviously that there are some sort of floods which occur in these months where it's mostly storm surges, but the majority of the flood days are still occurring when the tides are highest, even though this is a location which is generally pretty stormy, all things considered. And so I guess another way of viewing this is that day-to-day extremes require rare storm surges at Lakes Entrance. So there's not enough. So this product shows the probabilities of there being flooding on a particular day with sort of a normal storm surge climatology. And so what this means is that these are sort of the days with the highest tides each year. But there's still only like 6%, 5 or 6% chance that there's flooding on that day. So you need like a top 5% or top 6% storm surge to lead to flooding on those days. And this is reflected in here is that for this 99th percentile, which is what this calendar is looking at, flooding risk at the 99th percentile, you can see that there's a reasonable sort of, I guess, range of values. And sort of the grey lines are like 1,000 sort of simulations of storm surges, that most days you can end up with a chance of exceeding this 99th percentile with sort of a normal enough storm surge happening. If you go to a location like Ballina, which is much more tidal, then you start seeing daily probabilities of flooding of like 80-90%. And this occurs for two reasons. One, the tides are higher, so you've got a stronger modulation of the sort of probability that a storm surge, or basically how big a storm surge you need for flooding to happen. But then you also, in general, have much smaller storm surges, and so you have, in general, flooding is much more tidally driven. And so you can see this in this plot. We're looking at where the 99th percentile sits relative to the tide level, and then sort of a range of different storm surges. And this event here, this observed event, is one that is this compound flood event that we're going to look at. And so that was well outside sort of the normal range of variability in Ballina. If you have an extreme tide to surge ratio, such as in Broome, which has 10-metre tides, there are a very small number of days each year where a storm surge with historical precedent can cause flooding. And so this is an extreme case, but it's instructive, because what it means is that actually, even if you have a tropical cyclone in Broome, it probably won't cause flooding, or at least coastal-driven flooding, unless it happens to occur very close to the highest tide of the month. And even then, it probably has to be within cyclone season, which is sort of when these peaks are anyway. But that's worth keeping in mind as well. So there's sort of, and I guess this is sort of, I guess the corollary of all of this is that tidal modulations of sea level means that there's a lot of near misses. And this is important when you start thinking about understanding what sort of a potentially worst case storm surge might be, because you probably haven't observed the worst case. So here's an example of Townsville. There's two different metrics for storm surge here. One is the skew surge, which is the difference between the daily maximum water level and the daily maximum tide. And then the other is the non-tidal residual, which is the instantaneous difference between the observations and the tide. So the difference between the black line and the grey line. And you can see here that this was associated with a non-tidal residual of over 2 metres. but it only resulted in a skew surge of about 1 metre. So in other words, there was a 2 metre storm surge, but once you accounted for the fact that the storm surge didn't coincide with high tide, the water level recorded on that day was only 1 metre higher than it would have been without sort of under average weather conditions. And so this was still a significant event in Townsville, but it would have been a lot worse if the storm surge had happened about 4 hours later, when it coincided with the peak of the tide, which is sort of, or 7 hours later, probably, actually, looking at where that line is. But you get the point. And so here's another example, and this is from Darwin, which again has a very large tidal range, and this is Cyclone Tracy, which was a significant event, at least wind-wise, for Darwin. And in this case, the storm surge did actually coincide with high tide, but it coincided with a neap high tide, which was substantially lower than the high tide later in the month that was the spring tide. And so this is why these within-month variability of tides are really important too. And so this event was a non-event in terms of sea level as well, even though it was a large storm surge and even though it coincided with high tide. The other thing that can get complicated is that when you add stream flow into the mix, tides and stream flow modulate each other during compound riverine coastal floods. And so here's an example from Ballina with some work that my PhD student Jane Ewan has been working on. The sort of the yellow colour is the tide, the black colour is the observations, and then the purple colour is sort of the difference between them. And what you can see is that there's actually an oscillation in this residual, and that the tidal rate, the range of the black values when there's the flood around the 29th of January are much less than the tides at that same time. And this is because the riverine flooding actually reduces the tidal range within the estuary. And so you get this, I guess, illusory tide of that. You've sort of got a higher non-tidal residual on the low tide because you can actually get more water coming through the system when the water level's lower, because it can flow out more easily, I guess, in a really simplistic sort of way. And I guess moving on to the last part around present-day compound flooding occurring with fewer contributing factors under sea level rise. This is this Ballina compound flood from March 2022. So we've got the observed water levels here. We've got the tides in black, the breakwall, which is the gauge here on the breakwall, surprise, surprise, and then Missing and Bridge in red and Burns Point in black. And the impact level, we sort of assessed that the water levels in this CBD area was sort of between the red and the black. So this is sort of what this dashed black line is. So you can see what impacts were associated with that dashed black line of water levels here. And then you can compare this to this 2014 coastal flood, where all of the locations had the same water level during that event. But if you add 70 centimetres of sea level rise to these lower events, you actually reach this level that you had in 2022. And similarly, if you increase the tides by 90 centimetres, you get the sea level that you had in this 2022 event. And so what is currently a compound event, which can only occur when you have significant stream flow, will occur just due to coastal processes under 70 centimetres of sea level rise, and just due to tides, one coastal process under 90 centimetres of sea level rise. And so these events don't become compound events anymore, they just become events. And this sort of leads into this idea around historically significant floods become very common soon after they become common. Because once tidal flooding emerges, once you have these exceedances of the thresholds by tides alone or by coastal processes alone, you very rapidly increase the frequency of flooding. And so we looked at a study along the east coast of Australia with official flood thresholds that the Bureau have defined, and compared those flood thresholds to sort of the highest astronomical tide over a 20-year period, the annual highest tide, and the monthly highest tide. And what we found is that 30 of the locations have an offset between the minor flood level and the highest tide of less than 70 centimetres, which means that, like the Ballina example, you would expect these locations to have sort of tidal flooding at a minor level with 70 centimetres of sea level rise, which most jurisdictions in Australia are planning for by the end of the century. So of these 30 locations, 11 have less than 20 centimetres between minor flooding and the highest astronomical tide, which means that a sort of half-decent storm surge, particularly on the east coast associated with coastally trapped waves or sort of onshore flow, you can quite easily get a storm surge of 20 centimetres. You can actually get exceedances of these official flood levels without even needing to have any stream flow at all. And this is actually leading to discussions internally at the moment about sort of our estuary warning services and how we can adapt them to account for the fact that sea level rise now means that we are seeing exceedances due to coastal processes at gauges which have historically only experienced sort of flood threshold exceedances during compound events. And I guess the second piece of this is that there's not very much of a difference between the highest tide and the annual highest tide and the monthly highest tide. In fact, along the New South Wales and sort of southeast Queensland coast, which is what's shown here, is less than 20 centimetres to go from one tidal flooding event to having a tidal flood event every month. And so from an adaptation perspective, this means that you probably need to be anticipating these changes before they emerge, because sort of towards the end of the century, 20 centimetres of sea level rise doesn't give you that much time to plan. And so changes in tidal range can also change the relative importance of coastal versus riverine coastal floods. And so this is a different example from Lakes Entrance, but it also highlights that, I guess, the way that we engineer structures or coastal management techniques can impact coastal hazards and can impact compound hazards as well. So Lakes Entrance saw a reduction, a sort of a reduction in tidal range from the 1970s to the early 2000s. And it was then decided that they wanted to dredge the channel so that it would be deeper to allow for boats to more easily pass through the entrance into the lakes. And so this resulted in an increase in tidal range or a return to the original tidal range, whichever way you view it. But what this means is if you've got a bigger tidal range, you've got higher high tides and lower low tides. And this has two impacts. The higher high tides mean that smaller storm surges can cause coastal flooding, which is what we've seen in Lakes Entrance. The lower low tides, though, do mean you get better drainage of stream flow as you get a deeper entrance more often. And this is a finding which has also been observed in the Columbia River in the US, where less deep entrances make much higher flood peaks because you just can't get the water volume through the entrance. And so what's important about this is that dredging a channel has the effect of making flooding less compounding but more coastal. It doesn't mean that compound floods can't happen, but it tips the balance more in favour of the coastal processes over the riverine processes in causing coastal floods. And I think one of the questions that I haven't answered in this talk, and I think part of the reason for that is that we don't necessarily have a good answer, is if future high tides lead to the same impacts as today's compound floods, what do future compound floods look like? And there's a reason why this is complicated in Australia, and it sort of comes back to this plot. You shouldn't really be increasing all of these values by 90 centimetres because the stream flow contributions are tide dependent. So if you increase the tide level, the way that the stream flow responds going through the system will be different to what it was before. And so we don't, and my understanding is that the general idea is that it will be somewhere between, like it will be up to the amount but not probably equal to it. So for example, it might be that a flood peak increases 50 centimetres under a 90 centimetre sea level rise scenario. And so you've then got this challenge of understanding, well, what are the future compound floods? And that would be something which I would be interested in talking to people about if that's something that you're working on. And I guess to sort of help answer this question, and this I got minor revisions back on this paper today, we've been developing an estuary data set which has much better spatial coverage of estuaries in Australia. It's definitely focused on quantity of data rather than quality of data. But you can see that we've sort of got 600 gauges with data in sort of the recent years, which hopefully will help I guess, understand this relationship between the peaks of compound floods and the tide levels at which they happen, which I think sort of hold the insights that we need to help answer this question. More generally, this is a plug for something which is sort of just starting up. The IAPSO Commission of Sea Level and Tides is the successor to the Commission on Mean Sea Level and Tides, if people know what that is. One of these involves a subgroup on sea level extremes, which I'm leading. The mandate and activities involve promoting scientific research and community engagement, coordination with other bodies, and producing scientific and technical outputs. So please get in touch if you're interested in joining or finding out more or would like to nominate somebody to join. That's also encouraged. Thank you.